Hi everyone, my name is Yuke and I come from the University of California, Merced. And today I will present our paper, Understanding how Interconnects with an extensive benchmark survey. So this is the content of my presentation. I will start from the background introduction, then introduce Interconnects with survey in the paper, and then go to the benchmark part and show some experiment as an example. And finally, I will summarize what we did through this work. So with the increasing volume of data and high demand for large-scale workloads that run across the nodes in the data center and HPC clusters, different types of advanced interconnect have been designed to meet the requirement of like high bandwidth and low latency communications. For example, the frequent data communication in the large scale deep learning, big data, and microservice distributed workloads and applications. And with the development of hardware technology, the interconnects are upgraded from the conventional 10 gigabits per second to the advanced 400 gigabits per second, with multiple programming models and protocols to accelerate the internal communication. The interconnect matter because of its impact on the scalability and the performance of applications and workloads. With the development of the interconnects, there are several issues that researchers need to pay attention. First, for the different generations of hardware, they need to re-evaluate the performance to design like proper systems and based on the improved data transfer rate. Second, they should separately and carefully characterize the performance of different types of workloads on the new generation interconnects. Therefore, we believe that this is the high time to investigate the performance characterizations of interconnects in the modern data centers and HPC clusters through standard benchmarking experiments and under different applications and workloads. And the figure shows the scope of this paper. This paper surveyed various kinds of hot interconnects and associated representative benchmarks with a bottom-up approach. And from the hardware interconnects in modern data centers and HPC clusters to micro benchmarks on their network primitives and mechanisms. Finally, to the application level benchmarks running on diverse networks. In addition to the traditional Ethernet, there are multiple advanced interconnects have been developed in recent years. We surveyed 7 well-used interconnects on the cluster and data centers based on the open source materials, which include the conventional interconnects like Ethernet, InfiniBand, OmniPath, Slingshot areas, and some proprietary interconnects such as TOFO-D and VXI. And also we gave an overview and comparison of their features. For example, how large the bandwidth can achieve, how fast the latency they provide, and what programming model they support. More details can be found in our paper. To evaluate various interconnects, there have several macro benchmarks can be used. Typically, the real performance is hard to achieve the advertised number on internet. It may be like influenced by several fractions. For example, the latency for small message size would be different from the one for large message size. Therefore, when a researcher or developer try to deploy the system on data center and HPC cluster, using micro benchmarks to characterize the interconnect can give them an overview of about the network characterizations and guiding their design of system. We surveyed 6 micro benchmarks on different interconnects with multiple performance metrics. For example, what they can measure, which programming models they support, which transport protocols they use, and some other features. Through this table, a researcher can quickly target which one can help them to characterize the interconnects on the machines they will use and tune an improved system based on the hardware characterizations. Though there are diverse types of workloads and applications running across nodes in the data center and HPC clusters, they all need efficient data communication through the interconnects because different interconnects may show different characterizations even on the same workload. For example, the RPC application with Ethernet-based communication and with InfiniBand-based communication may have 10 times of the latency gap, which could introduce a huge impact on the behavior of the application. Therefore, using benchmarks to evaluate the applications that run on a specific hardware is crucial for researchers and developers. To represent a wide range of applications and workloads running across the nodes in data center and clusters. As you can see in the figure, MPI and PGAS is for the HPC area, and the GPU applications for the AI area. And key-value storage and RPC is for the big data area, and finally the microservices for the cloud area. And we surveyed 25 application-level benchmarks across 7 well-known applications and workloads running in the data center and HPC clusters, and gave each detailed descriptions about categories, metrics, and other features. Except for the introduction and description of the interconnects, we choose several well-designed and maintained micro benchmarks and application-level benchmarks to measure the performance of different interconnects. The test bed is shown in the table. We run several benchmarks on 4 different test beds with different interconnects. And in the following slide, I will show 3 experiments as examples. The first example is a latency comparison of micro benchmark. In this experiment, we used 2 programming models, RDMA and socket, with 2 different micro benchmarks, netperf and perf-test, on 3 interconnects, the 10 and 25 gigabit per second Ethernet and 200 gigabit per second InfiniBand. Through the performance comparison, like we can see, an interconnect with higher link bandwidth does not always give you lower latency. For example, the latency comparison between Rocky on 25 gigabit per second Ethernet, which is the purple line in the figure, and the IPOIB on 200 gigabit per second InfiniBand, which is the blue line in the figure. And the second example is the bandwidth comparison of micro benchmarks. In this experiment, we use the same setting as the previous example. In the figure, the Rocky, which is a purple line, saturates the interconnect bandwidth after the message size achieves 1 MTU. However, IPOIB, the red line, cannot saturate the bandwidth, the 200 gigabit per second bandwidth because of the TCP protocol stack overhead. And therefore, an interconnect with higher link bandwidth does not always promise bandwidth saturations. The third example comes from the application level benchmark. In this experiment, we use one of the PGAS model OpenSHMAM as a workload, with OSU micro benchmarks for 2 collective routines, broadcast and all-to-all on 8 nodes, with 2 different interconnects, 100 gigabit per second omnipath and 100 gigabit per second InfiniBand. Though these 2 interconnects have the same link bandwidth, but they show different latency numbers when the message size change. For example, the InfiniBand shows a lower latency number than omnipath in most cases, except for the all-to-all operation in small message size. And when the message size is large enough, like 1 megabyte, we can observe that the latency of OmniPath can achieve 2 times the degradations of the one on InfiniBand. Finally, I will summarize what our survey paper did. We performed an extensive survey on advanced hot interconnects and associated representative benchmarks from both micro levels and application levels. Based on that, we picked some well-used benchmarks and performed a set of experiments on real hardware and discussed their performance characterizations. Through our work, we shared our observations on improvable aspects of existing benchmarks to help the further benchmark designs. So that is all of my presentations. Thank you, and feel free to ask any question.